Good morning, everybody. Thanks for joining us. This is the CEPHaS team holding our virtual conference as we're nearing the end of our project. I am Alessia, I am the project manager, and in the room with me there is Professor Lark, who is the principal investigator for the CEPHaS project, and Dr. Benja Browns, who's the deputy project manager and deputy working group lead for the hydrogeology team. We are very pleased that you are all able to join us this morning, and we will be sharing with you some of the findings that we've had and we've found since this fantastic project started back in 2017. The conference will be held over 3 days. Today is our first day. As you can see, we've got things lined up until 11 a.m. GMT time. There will be a couple of external speakers that have kindly agreed to come in and talk for the CEPHaS conference, and then 4 talks by our team members. There is a break scheduled for 9:45 until 10 GMT time, and this will be your chance to step away. I'm afraid, being a virtual conference, we have no coffee or mingling facilities today. Just a little bit of housekeeping. If you have any questions for the speakers, if you could please use the Q&A facility. You will see it on your bar at the top or the bottom of your screen, of your Zoom screen. If you could please put any questions in the Q&A, and then one of us will ask the questions to the speakers. And the chat, if you could please just use the chat if there is any general comment, or for instance, for introducing yourselves as you've been doing, that would be really good. Thank you. And now I shall pass the reins to Professor Lark to introduce us. Thank you.
Thank you very much, Alessia, and welcome to everyone. Thank you for joining us. So it's very good to have all of you here to hear more about the CEPHaS project and its outputs, to see team members and others, friends of the project and other people who I imagine have heard about this meeting via social media and other sources. So you're all very welcome. I hope you will find the programme interesting and stimulating. I thought I would begin the welcome with a few observations about the CEPHaS project for the benefit of those of you who don't know about it or don't know very much about it. The CEPHaS project is one of a number of projects in the Global Challenges Research Fund from the United Kingdom Research and Innovation, and it's part of the GROW consortium, which is concerned with the development of and strengthening of research capacity in partnerships between Global North and Global South to address key challenges. And the CEPHaS project is concerned with the physical sciences that are key to understanding conservation agriculture systems and how they work. And when I say the physical sciences, I mean things like soil physics, biophysics of soil-crop interactions, and then the relationships between water in the soil and water in the ground, groundwater sources, which are so critical to many communities in Africa and elsewhere. Hence the title of this virtual conference, Understanding Conservation Agriculture, Soil, Crops and Water under Climate Change. And the CEPHaS project is a collaboration between scientists in Zimbabwe, Zambia and Malawi, as you can see on the map on the front of our slide, along with partners in the United Kingdom from the British Geological Survey, University of Nottingham, Rothamsted Research and the Liverpool School of Tropical Medicine. Now, conservation agriculture, as you will know, has been widely promoted and investigated as a response, as a set of innovations and interventions to respond to the challenges of making cropping sustainable in a changing climate. So among various approaches to climate smart agronomic systems, conservation agriculture, in which we avoid disturbing the ground by tillage, in which we cover the soil with crop residues or other sources of biomass, both to protect the surface, to increase its organic status, and in which we use different mechanisms to diversify the cropping system, such as rotations or intercropping. This has been found, and here we have a nice example from some colleagues of ours. There's Dr. Alan Chimungu and Dr. Ivy Ligowe at the plots in Chitezi, near Lilongwe in Malawi. And there you see on the left of the photograph, conservation agriculture plot next to a conventional plot towards the end of what had been a rather dry cropping season. So we know something about the yield responses to conservation agriculture and something about soil property responses. And what CEPHaS wanted to do was to understand in a more holistic way what the impact of these practices are on soil water dynamics and therefore on the resilience of cropping systems, and in particular on the interaction between water in the soil and groundwater. What is the impact of such a change in land use practice on groundwater recharge? Because through the discussions within the project consortium, we felt this was critical for policy and extension. But a limiting factor to addressing these questions is research capacity in the relevant physical sciences. And this has been true in Africa, but it's true globally. I think we could say that soil physics has been something of a Cinderella science, not given the investment that it's required in order to keep up with the important and demanding questions that climate change faces us with. So we were concerned with developing capacity globally in our network to address these problems. So we came up with this conceptual approach, and this partnership between our three institutions in Central Africa, Southern Africa, and the institutions, 4 institutions in the United Kingdom, was a long-standing one which went back before CEPHaS, looking at other aspects of conservation agriculture, in particular in respect of crop nutrition and crop quality. So we got together and extended those discussions to think about the processes involved in water, infiltration and retention in the soil, retention in the profile, movement down to groundwater. What's going on and how might interventions affect this? And the question is, of course, how can we observe this system? And how can we observe and link together its different components? So in that central block, we see approaches to measuring soil water properties, both field observations and laboratory measurements. And at the bottom, established approaches to looking at recharge, looking at groundwater levels and groundwater quality. How do we link those? Well, innovations at the British Geological Survey in terms of low energy, low cost electrical resistivity tomography systems for visualizing water in the subsurface provided one obvious approach to take to connect these components of the system together. And then to integrate that, we need information on the lateral variation of soils, and we need statistical and process modeling to put it all together. And then finally, we need economists, agricultural economists and others with an understanding of cropping systems to provide an overview. So that was the CEPHaS vision. And you can see there the CEPHaS team, the organizations involved, and then at the top right, those of us who assembled in Lusaka now over 4 years ago to put the project plan together in detail. A year later, we met in Lilongwe at the Luana campus in 2018. And then at the bottom, 2019, the last time the whole CEPHaS team were able to meet together back in Lusaka. And as you can see, we were still full of energy and enthusiasm 2 years on, and not even the pandemic put an end to that. And just a few photographs from the team in action in the field, talking to farmers on the top left, Kabaleka in Zambia, where we were observing groundwater under systems in use, looking at groundwater, looking at soil samples in the laboratory for measuring water retention. There in the top right, the team lowering electrodes to 3 meters into the ground at Chitezi for visualizing water in the subsurface. The bottom left, stakeholders being shown the soil physical measurements being made in the field. On the bottom center, back in Nottingham, team members looking at advanced methods in X-ray computerized tomography to observe the structure of the soil, the contrasting treatments. And then at the bottom right, one of our stakeholder events, the number of stakeholders and team members in the field talking about water under agricultural systems. Themes then for this week. Today, we're focusing largely on conservation agriculture impacts on soil and the crop. On Wednesday, soil properties and soil information will be our main focus. And then on Friday, the focus will be very much on water in the subsurface and on capacity strengthening, both in hydrogeology, but across the CEPHaS programme, as well as some input from the farming systems and economics team, giving their overview at the end of the programme on how all this adds up to messages for farmers. So I hope that everyone here with us today will be able to join for all 3 days of the meeting, and a reminder that you need to register for each day separately on Eventbrite. Now, we're very grateful to our opening keynote speaker for this Monday morning, our first morning of the conference. Our keynote speaker is a long-standing friend of the CEPHaS project, Professor Martin Broadley. Martin is Science Director for Sustainable Soil and Crops at Rothamsted Research, Rothamsted, of course, being one of the partners in CEPHaS, and he's also a Professor of Plant Nutrition at the University of Nottingham. His particular areas of interest are in crop nutrition, biofortification, approaches to micronutrient deficiency and hidden hunger. And out of all that, he has developed over the years an interest in research capacity strengthening and how it can be integrated into research programs and the development of educational programs too. So with no more ado, I'd like to thank Martin again for coming to speak to us this morning. And I'll hand you back to Alessia to continue to chair the session and pass you on to Martin.
Thank you, Murray. Okay, we will stop sharing our screen and we will ask Martin to start his talk, if you may. Thank you.
Thank you, Alessia. Can you see that okay?
Yes, we can.
Excellent. Okay, thank you, Alessia. Thanks very much, Murray, for that very kind introduction, and thank you for inviting me to speak today. It's a real pleasure to be able to give the opening talk this morning, and thank you for that. I'm going to talk a little bit. I'm going to go a little bit back further in history than Murray with the photographs today, and I'm going to start by talking about a project that many of us were working on together, funded by the Africa Capacity Building Initiative, which was supported by the UK's Royal Society and Foreign and Commonwealth and Development Office, where we were working on a project called Soil Geochemistry for Agriculture and Health, which started in 2015 after a couple of years of development. And one of the main drivers for this particular programme was some of the asymmetries in terms of research capacity that we see around the world. And I haven't updated this map for a couple of years, but this is an interesting map showing the number of researchers, including PhD students per million inhabitants from around 2018. And you'll already see the disparities in numbers across the globe. So if we go and have a look in North America and Europe, Australia, there's around 5,000 researchers per million inhabitants. If we look in Africa, sub-Saharan Africa in particular, then often there is fewer than 100, and often we're in double digits. Here's a little bit more detail on that. Obviously, the situation is heterogeneous within Africa too, but the numbers of researchers and active PhD students is one at least, or maybe two orders of magnitude smaller than we see in many other parts of the world. And that's what this investment was, in its own small way, trying to help support. So we began this project. It actually started in around 2013 with partnerships with Malawi, Zambia and Zimbabwe that were driven very much by existing relationships between our partners in these countries. Lots of different institutions and government research institutions and university departments collaborating in each location. This is an older photograph from our first network training event from September of 2015 in Harare. We're all looking very happy there. This was as we started to design what was going to happen within the soil geochemistry project. And one of the main components of the investment was to support PhD training for now Dr. Belinda Kaninga from University of Zambia, Dr. Grace Kangara from University of Zimbabwe, and Dr. Ivy Ligowe from Lilongwe University. We also had funding for additional students, and here Dr. Felix Phiri from Malawi, from the Ministry of Health, was one of the aligned PhD students that began at around the same time. And as Murray has already indicated, one of our main interests was looking at crop nutrition and quality. And we took advantage of some of the excellent resources that were available in the network. And here's Ivy on those conservation agriculture plots. This is from 2017. And Ivy spent time looking at the effects of different treatments on the maize grain quality that was growing on these plots, and in particular, micronutrient quality of the maize grain growing on these plots. Belinda's project was in Copperbelt. Belinda was focusing very much on some of the trace elements of concern to human health arising from mining operations, and also looking at farmer interventions such that these could be mitigated in terms of flows of these both micronutrients and toxic trace elements into food systems. And then finally, Grace, her project was focusing on agronomic biofortification, in particular looking at zinc and iron micronutrients, and working again with smallholder farmers, looking at ways to improve that through both fertilizers, but also wider integrated soil fertility management activities. We developed a rather convoluted and complex theory of change, which was quite an interesting exercise in itself, which I won't go into detail, but it was certainly an excellent learning experience for myself, and I think others currently in the CEPHaS project as well, in terms of how we mapped what we planned to do and what change we wanted to make. And overall, it was a really excellent project. It's coming to an end shortly now. We've had various no-cost extensions, but all of the PhD students are now successfully defended and through their PhDs, and we've got quite a few papers and blogs and talks. In particular, there was a focus on some of the laboratory side, particularly from the soil chemistry side, which I think complements the soil physics work that has been going on since with CEPHaS. And that includes training fellowships for analytical chemists within the different institutions. It's led to, I think, career development for some of us involved in the project itself. And again, more importantly then, the sort of outcomes level, where we've been able to see additional investment in new PhD students and training programs, and substantial new investment in R&D projects, which themselves are leading to some interesting outcomes. And I think it's fair to say that CEPHaS has been a really excellent outcome of the project. And this, as Murray said, started in 2017, building on the networks that were under development. And it was very exciting to see this project come to life in 2017. You're going to hear about that, obviously, over the next week. In terms of a project that also arose from the capacity training network, I'm going to just mention Geonutrition Project, which was a project funded by primarily the Bill and Melinda Gates Foundation, but also, again, the GCRF funding from the UK, which was a large collaboration involving research institutes in Ethiopia and Malawi, and led in Malawi by Luana and Dr. Nalibata, who I think is with us today and involved heavily in CEPHaS as well. And this involved lots of surveys. It built on some of the training activities that we developed in the network and also in CEPHaS. And these are some photographs from April 2018, when the field teams from Malawi were being trained by colleagues from Luana, including Innocent and Ivy, and colleagues from the UK, including Deriva. And this was the moment on the lower photograph when the field teams started to move from Lilongwe into the field to try and capture soils and maize grain across a very short sampling window of 5 or 6 weeks. And this little animation just shows those teams as they moved through Malawi, sampling soils and grains. And this was a sampling design that was developed by Murray and colleagues, and it was designed explicitly to link up with some of the public health sampling that had been going on a couple of years prior to that, including the demographic and health survey. We conducted this in 2017, 2018, and into 2019 in Malawi and in Ethiopia. And these are what the cereal types look like from this particular sampling design in those two countries. So Malawi here is covered in blue triangles, which indicates a maize sampling location. The Ethiopia map on the left has lots of different coloured triangles on, representing the more diverse cereal systems of Ethiopia that was sampled as part of this activity. And I guess the project highlight for Geonutrition came earlier this year when we were able to publish the outputs of this particular, or these surveys in Nature, looking at how the micronutrient quality of the cereals varied geospatially across Ethiopia and Malawi. And we have lots of these types of maps that have been developed, including by colleagues from UZ and now working in the UK. And this is a map developed by Chris Chagamira. And this is showing the dietary selenium supply arising from wheat and teff in Ethiopia, such that the areas in yellow here, an individual is likely to be getting less than 20% of their dietary amount of selenium, which is an essential micronutrient. And if we move over from the west towards the east of this region here in Ethiopia, which is the Amara region, we can see now that the average requirement of selenium is now in excess of 80% when we move over to the east. And this is showing what the effect of different soil types and different landscapes are having on the micronutrient supply in food systems. And we've looked at this for several different micronutrients, say, including selenium and also zinc and iron and calcium. And building on this work, and again, building on some of the ideas that have been developed in CEPHaS and in the previous training network, we've been able to develop this work into delivery of decision support systems. And this is an example called MAPS, which is looking at how we can bring together multiple data sets, including new data, but also existing secondary data sets into ways which can support both policy interventions, but also innovations and other farming system interventions. Again, with very strong contributions from Luana, also British Geological Survey in this particular project as well. Finally, I'd just like to say that the Geonutrition work, then we were very fortunate to be able to extend this into Zimbabwe with the support of UZ. And we were able to secure some money to try and translate some of these ideas into a Zimbabwe context. And this started towards the end of 2019. It's obviously been very badly affected by COVID to some extent, but remarkably, the teams in Zimbabwe have been able to maintain the work and keep the work going, and hopefully we'll shortly be able to report a successful project in Zimbabwe. The idea here was to look at a pilot surveillance program to look at micronutrient deficiencies in Zimbabwe, including biomarker surveys. This also to sample agricultural materials, soils, crops, forages, again using a particular stratification design and questionnaires so that we can look at what micronutrients are in the food system. And again, there was an institutional and individual research capacity component, including new PhDs, including in the Department of Nutrition at UZ, also in the soils and agriculture groups there as well. And so again, a lot of the lessons learned regarding training were implemented. This is some photographs from February 2020, shortly before the effects of COVID meant that we became locked down. And here's Grace on the right, delivering some of that training. And here's one of our sampling designs for Mutare district that we developed, looking at land use cover and then optimizing the spatial coverage of samples across this district. And we focused on 6 districts for the agriculture survey and 3 districts for the micronutrient biomarker survey. And then lots of in-field sampling of soils and either standing crops or field stocks and granaries. So hopefully next year we'll be able to report on that on that particular project. And I'd like to finish this and with the same photograph that I showed at the start, which is a group of the ACBI team in Chitala in Malawi, close to Lake Malawi, where we were being given a phenomenal lecture on vertisols by Dr. Max Ligowe from Luana. And there are several people, I think, in the audience today that were on this photograph, which was taken in September 2016. And I think this was a very memorable day for me because, firstly, it brought the team really together in terms of seeing some of these phenomenal soil pits that had been prepared for this training activity. But also, it was the time when the CEPHaS project was coalescing and coming together shortly before it started in 2017. And I think it was at this moment in September 2016 at this meeting that we realized that these networks and these capacity building activities were going to be much longer lived than the networks themselves. And so with that, I would like to say thank you very much again for inviting me to speak today. And I look forward to hearing more during the next week. And apologies that I will have to drop in and out, but I'll try and attend as many of the talks as I can. And thank you very much.
Thank you, Martin. That was a really nice talk. Thank you. Sorry, I'm not on the screen. I don't know if there are any questions that are coming, Bencher. Is there nothing? No, I think you were very exhaustive in your presentation. There is no need for further clarification. So I'll just pass the reins to Murray again, who is going to introduce our next speaker, perhaps, unless he has a question for Martin himself.
Well, I always have questions for Martin because his talks always throw up lots of interesting lines of discussion. I suppose, Martin, one question that I do have is, over the period of this particular group of projects and partnerships, where you think the main pinch points are in terms of getting teams to work together effectively to deliver the kind of results that stakeholders need, but doing so in an equitable way across all the institutions involved, and developing ways of working which really offer perhaps more creative ways of doing things together in the future.
Thanks, Murray. That's a really good question. I'd say probably the biggest challenge that we've had, and I suspect that CEPHaS has had as well, is in terms of some of the timescales that arise. So often the proposal development has quite a nice amount of time for people to think and plan and interact, and then often decisions on funding arise, which then require rather rapid implementation, and often funding cycles don't necessarily coincide with cropping seasons and field activities that are needed. So I think one of the biggest challenges is then establishing and knowing where the trust and how that can be developed within the consortium. And so I think the experience from my point of view is having these long-standing relationships and having this trust within the system has proven to be invaluable when we've been doing this type of work, because obviously with survey type work, and particularly at national scales, we've had to be able to move very, very, very quickly. And so what we've found is those relationships and particularly relationships with individuals who are themselves very plugged into national and international networks has proven to be critical in developing and delivering these projects. So I think that's been the main experience that I would say. I think the solution to that is difficult, but hopefully if we continue to work together and if we continue to make these representations and deliver this message to our respective governments and other funders, that we can hopefully build some longer term research programs and partnerships where perhaps some of those pressures can be alleviated a little.
Thank you, Martin. Alessia, is that something Q&A?
Yes, we have a question. Would you like to read it out, Murray, or do you want me to?
Yes, so there's questions from Russell. I think it's actually overlapped quite a bit with what Martin's just said. He says, you mentioned how working networks have led to a natural flow of projects. What do you see as the future for research in this area with regards to funding and keeping these working relationships going? So I think that's very much what you just addressed.
Yes, if I could just add one more thing to that, Murray. Having just moved to Rothamsted in the summer, I'm sort of just getting used to some of the research institute landscapes again in the UK. And I think particularly from BGS and Rothamsted's point of view, I think we can work within our organisations and within the research institute landscape to make sure that we make the links and the connections between some of the strategic funding that comes into our organisations for national scale projects, and think about how we can work together to develop opportunities for uplift projects, particularly in the international area. So we're going through cycles at the moment, and I know BGS are as well. And so I think that's something that we should pay particular attention to in this cycle.
Thank you, Martin.
Okay.
Right.
Shall we?
Okay, yes. So if we can then thank Martin again for that contribution, for stimulating and very interesting contribution indeed. And now we start with the CEPHaS team programme. And our first talk is from a group, a cross-working group one, the Soil Physics Working Group in CEPHaS. And members of this team come from all three African partner institutions in the project along with others. And they're going to be presenting jointly across all three experiments that we've been working on. So I'd like to introduce the speaker who will be presenting, Moombe from University of Zambia. Nyanda's a specialist in soil and irrigation systems with his interest in soil physics and cropping systems, and has been contributing across the areas in CEPHaS at UNZA. But we'll be talking in particular today to our first topic, which is on soil moisture retention curves under reduced and conventional tillage. So thank you, Meander, and we're looking forward very much to hearing your presentation on behalf of your Working Group 1 colleagues.
So good morning, everyone. Thank you, Mary, for the good introduction. And I would love also to thank the CEPHaS team for according me this opportunity to present some of the findings from our research sites. So can everyone see the presentation?
We can, yes. Thank you, Meander.
So I'll be presenting on the data we have so far and what we are seeing from soil moisture retention curves that we have done across 3 sites. That is Yempe site, Chiteze, and Ndomboshawa in Zimbabwe. So Chiteze is in Malawi and Yempe in Zambia. Just to begin with, maybe a little background on the soil water retention. So maybe for someone who might be wondering what it's all about, it's simply a relationship of soil water content and the potential at which it's retained in the soil. So this is important, especially for water uptake in plants. Basically, if the potential is low and you have a lot of water at that low potential, then you'd expect the uptake of plant would be easier rather than at high potentials. So this can be measured in the lab or directly in the field if you place matrix potential sensors and water content sensors together. But for our work, which we're presenting today, did it in the laboratory. So measurements were done in the laboratory. And then there are quite a number of models which you can use to describe that relationship. But for our data, we used Van Genopten. Yeah. So what you see is just an example of how the soil moisture retention curve looks like. So there are various and different shapes, and to this there are various fitting parameters which are used to describe the shape of the water retention curve. And these parameters are what we were trying to calculate using Van Genopten model, and then compare these to see whether we have differences in our treatments. So the methodology we used was the water hanging column method. Of course, this is much easier. The height of the water in the column, we simply tell you the potential. If you can see in this picture, which I hope it's clear enough, it's about a 3-meter high tower, which we have installed in our laboratory at Onza. Then you place your samples, of course, on a plate, and then you keep changing the water potential. And also at the same time, determining what would be the water content in the samples. So then you have that relationship of the potential and the water content. So as you can see, this one, if you have to measure higher tensions, definitely, then it has to be a very tall tower. And it will become more risky for this guy who's on top measuring the water content and changing the pressure. So at higher potential, then you would use this pressure apparatus which you have in the laboratory. And then, of course, it has a compressor that you can use to apply more pressure to the samples. Yeah. So the sites we have in Malawi are quite older. This has been a long-term experiment under CIMMYT, and they have quite a number of treatments, but for the CEPHaS project, we were mainly looking at these 3 treatments where they had only maize in a conventional tillage system, and in conservation agricultural system, and then maize with rotation with velvet beans. At Liempe, it's a much newer experiment. This was established at the beginning of the project, so it's only been about 4 years now. Yeah. But of course, it's much younger. Yeah. And here we have only 2 treatments: a conventional one, where you have maize on its own, and the CA1, where we mostly just reap and don't plow everywhere, with an intercrop of soybeans. In Zimbabwe, there too we were looking at the conventional, where you plow everywhere, and the CA, where you don't till. So in this case, you just directly seed. Yeah. And this one too is a much older experiment. It's been going on for some time. So with the data, what we are seeing, of course, it's not conclusive, as we are yet to put in more to it. But from the initial data, in the Liempe site, we are starting to see some marginal differences. Whether these are real differences or artifacts, we're yet to analyze that. But it's also good to know that the Liempe site, when you come to its soils, is a little bit, anyway, all the soils are a little bit different across sites. But with the Liempe, mostly this was a compacted soil. So it's a promising result to see that just by using the CA there, we're able to start noticing some marginal differences. Maybe with time, then this could be amplified. So we were doing this analysis for 2 depths, one 0 to 5 at Liempe, and 5 to 10. Of course, you see much more of that difference in the 5 to 10. Whereas in Zimbabwe, on the Dombo shower site, which has been a long-term experiment, and not much differences are noticed. But you can also notice that the sampling band is a little bit wider. It's 0 to 10 centimeters, and then 10 to 20 centimeters. But also from literature, we know that sampling depth would also influence what result you would get from an experimental site, especially when you're looking at organic matter and the effects of it. Depending on the depth band you use, you might have a dilution effect. And maybe if we used a much smaller depth band, maybe you would be able to see something. So that's something you could consider. So just a visual. Sorry, I moved a little bit too far. So I should be here. Yeah. Visual representation of the moisture retention curves, which we are seeing at Liempe and at Dombo shower. So you can see at Liempe, the separation is a little bit more in the saturated zone, closer to there, and also in the 5 to 10 centimeters. And here in Dombo shower as well, in the 10 to 20, you see that similar trend. Yeah. So with the CEPHaS site in Malawi, this one is still also being analyzed as well, but you actually see that there could be some direction also indicating some differences in the two treatments, the CA and the conventional tillage. Yeah. So in this one, unlike the other ones, you see that these differences will be showing in the lower or the drier end of the moisture retention. Okay, so whether this is something, yeah, which is a different soil or just some artifacts, this is something which we still need to look at when we have the full data set. So to conclude, we can see some evidence, although not really that much, in the Zambian experiment of greater water retention, of course, when you have a low water potential that is close to saturation. Yeah. And, yeah, this maybe could be better looked at also if we include the soil organic matter data to explain. Of course, there is more data that we need to this. And in Zimbabwe also, there's also that evidence similar to the Zambian. But in Malawi, we are seeing the opposite end of the soil moisture retention curve having more retention under CA, like the two sites. But however, the data we have is just provisional, which we still need to compare, fully compare. So that's that with soil moisture retention curve and what we have been able to see so far under the working group 1, soil physics. So Alessia, I'll hand over to you.
Thank you, Mianda. Thanks for your presentation. I don't see any questions in the Q&A. I'm not sure if anybody is typing. We will wait for a minute. I don't know if Murray has any questions.
I do. In the meantime, while we're waiting for people to type in. So, Mianda, across all 3 sites, you're seeing at certain depths effects. So you're seeing changes at Dombashawa and at Liempe, which relate to the larger pores in the soil. There seems to be an increase in the porosity under the conservation agriculture at Liempe, actually greater porosity at that end of the water retention curve under conventional management in Dombashawa. But of course, what's interesting about that is that you're talking about pores which don't retain water against gravity. If you go to the tension roughly used as an indicator of field capacity, those curves are very close together. So while there isn't a consistent conservation agriculture effect, you're dealing with very different soils, and you're actually dealing with different conservation agriculture practices. In fact, they're broadly comparable, but not the same practice. So it's perhaps not surprising that you're finding different responses in different soils. What I think is particularly interesting is that you're seeing effects which would have implications, say, for the aeration of the soils, but in terms of the retention of water in the soil profile, suggesting that there's not much effect, that you're not getting much effect on that relevant porosity. So I think we must be a bit more positive about these results, because I think it's really interesting to see that there is a measurable effect, but that perhaps it's not having some of the impacts we might have expected in terms of water retention, although it will have other physical impacts and possibly also related to infiltration of water.
Yes, Mary, I agree with you. And the fact that we are dealing with a wide range of soils, that makes it even more interesting, because then you can be able to say that under such soils, we're able to see such a response, maybe in a shorter time compared to another kind of soil. And also you can now even begin to look at dynamics of really what contributed to that change. Since here we are mostly in common, you have minimal disturbance, and then at the same time additional organic residues. So you're simply trying to add some organic matter. Yeah, so you can really try to see also the movement of the organic matter. Is it moving down or is it remaining on top? Is it being incorporated? And then where are the differences showing? Yeah. So in this case, it's very interesting.
Right. Thank you, Nyanda. How are we for time, Alessia?
We've got a couple of minutes. There are a couple of questions in the Q&A, Nyanda. First one quickly, why did you increase the depth ranges at Domboshava?
That maybe Vangai or is Hattie with us might be able to help with that one.
Yes, I think he's better placed.
Yeah. Vangai, would you be able to step in, please?
Come on, Alessia.
The question on the Q&A is, why did you increase the depth ranges at Domboshava?
What was the reason?
The depth ranges at which we took the samples, right?
Yes, yeah. The choice of the depth.
We wanted to see the differences in depth, because for instance, the 10 to 21, that's where we see most of the root activities from the maize crop. So we wanted to see the difference in terms of if we take near the surface and just a little bit under the surface, because these soils are also prone to eluviation, where some soil particles can actually, clay particles can actually be washed down a little bit from the surface. So that was something related to that kind of process, because we tend to have a little bit of, these are sand loam soils, so we tend to have some little bit of more clay content as we move down the soil.
Thank you, Vangai.
And maybe just also to give a background to it, that, there wasn't really much of a, can I say, a deliberate plan to say we use 10 at Domboshava or 0 to 5 here at Ligowe, because also I believe this area of research is relatively new for most of us as well, because even though we use 0 to 5, how do you know 0 to 5 was the best for the kind of conditions we had? Maybe we could have even reduced the bands further to see a little bit much more of an effect from 0 to 2 and then 2 to 5 and like that. But it's also about the resources as well, and also it being kind of a new area as well. I wouldn't say that's something which we are routinely doing to reduce the dams, but I think this is something that's coming now. Anyway, I would stand to be corrected.
Richard's question.
Yeah. Just another question, Meander, and then I think we're going to move the rest in the chat for you to answer because we are due to start our next chat. But the last question for you. In Malawi, we appear to see lower groundwater recharge than we see in Zambia and Zimbabwe. Does this agree with the differences that you have noted in higher soil tension water content in Malawi?
Maybe you cannot really base on that one on what we have observed solely on the data we have, but to read we might need to incorporate more of the data from the hydrology team, because it's also a matter of the geology, like what is really the geology in which you have that experiment, because then that will tell you also much of the groundwater recharge.
Yes, I think that physical information will in due course be plugged into some of the models that the working groups are working with, and I would have expected, other things being equal, that would certainly be in effect. So that will be interesting to see. Thank you very much, Meander, for that very interesting presentation and for fielding questions. So we now move on to our next presentation for the session. And this is from the Zimbabwe team, and V.Mbanyele from UZ is the presenter for this talk. His title, on behalf of his wider team, is the Comparative Long-Term Performance of Conservation Agriculture and Conventional Tillage on Soil Water Dynamics and Maize Yield in Semi-Arid Zimbabwe. So Vengai is working at University of Zimbabwe. He's a research associate on the CEPHaS project and is also completing a PhD. He's interested in cropping systems and their agronomy, how soils and plants interact, and on integrated soil fertility management as a strategy for more resilient cropping. So thank you very much, Vengai. We look forward to hearing your presentation.
Thank you very much, Prof. Lark. Yeah, so as you heard, Vengai is my name. I'm from the University of Zimbabwe. I am going to present on behalf of the working group team. Quite a number of people there with the different experiences in research. Can we go to the title of the presentation is Comparative Long-Term Performance of Conservation Agriculture and Conventional Tillage on Soil Water Dynamics and Maize Grain Yield in Semi-Arid Zimbabwe. Can we go to the next slide? Alessia, next slide, please.
Sorry, Vengai, just 1 second. Can you see the slides? Yes.
Yes, now.
Okay.
So in terms of the structure of the presentation, I am going to start with the introduction where I introduce the experiment, and I will talk briefly about the CEPHaS project. I know Prof. Mari has already said something about the CEPHaS project, but I will try to buttress some of the points he was talking about, especially the research capacity of the local institutions. Then I will also talk about the methodology, how we measured the soil water content. Then I also dwell into the results and discussion. Then I will talk about the key message which we so far distilled from the results we got. Can we go to the next slide, please? So in the last 2 decades or so, there's been a growing interest of conservation agriculture across Southern Africa to try and provide a solution to the crop production constraints which are which are faced in the region, such as the increased incidences of intra-seasonal dry spells. So there's been also huge investment in CA research, conservation agriculture. Quite a number of organizations has been doing a lot of conservation agriculture research in Southern Africa, including CIMMYT, and quite a number of others like UKRI. So far, there is some experimental evidence which shows that conservation agriculture is performing better than conventional agriculture in terms of yield. However, there is a pertinent question with regard to what extent can CA be more resilient to climate change than conventional agriculture. In particular, looking at water behavior, there is a little information around that. So CEPHaS undertook to know more about this subject in terms of soil water dynamics in conventional agriculture and conservation agriculture. So there are some long-term experiments in the two countries which are already doing conservation agriculture experiments. So we undertook to do, under CEPHaS, we undertook to do some of these measurements to be able to find some answers in relation to soil water behavior. For us to be able to perform that task, research capacity of local institutions was greatly improved, both in the laboratory as well as in the field, for us to be able to measure such a very important factor. So can we go to the next, please? So in Zimbabwe, which I'm going to present the results on, in some other places, we are still doing some analysis and try to find out some trends. So in Zimbabwe, we did our experiments. We worked on the CIMMYT experiment, which was established about 10 years ago. And the soil type in the area is a sand loam, which is typical of soils you find in our smallholder farms in Zimbabwe. So we worked on the two experiments out of mainly the treatments are to do with the tillage as well as some addition of crop residues. In this case, we opted for conventional till and also for conservation agriculture, where 5 tons per hectare of crop residues was added. Then these treatments were actually arranged in a randomized complete block design with 3 replicates, and the plot size were 10 by 10, which is 100 square meters. Can we go to the picture there shows Dombo shower site? I think you have seen that picture from Mianda's presentation. Can we go to the next slide? So we did some field installations for us to be able to monitor water in the different plots, that is CAE and conventional tillage. We used the PR2 probes, which looks like, which is as shown in that picture, the top picture. So we monitored soil water content at different depths, which were 10, 20, 30, 40 schists, and up to 100 centimeters depth. So these PR2 probes were connected to a data logger, and we were logging at 1 hour frequency. So in other words, we collected the data automatically. We only visited the site once in a week or so to download the data and to see if there are any issues. So can we go to the next one? So in terms of the schematic view of the installed probes, remember we said we had 3 blocks. So the 3 blocks were as shown in that picture, in that schematic view. So within each plot, we had 3 probes, which were were located equidistant in a triangle format. Then all the probes from the two plots, which were adjacent to each other, were connected to one logger. So this was the case in all the blocks. We connected the conventional and the conservation agriculture plot together in a one logger. Can we go to the next slide? Then we also did some other key measurements, which are very important for us to see how the plants are progressing in terms of growth. One of the key measurement we did was the leaf area index. In other words, we monitored the leaf area development over time from the two plots, that is conservation agriculture and conventional tillage. Then we also measured the stomatal resistance using the porometer. In other words, to assess the level of stress to which the plants are exposed. And this is closely related to the availability of water or soil moisture in the soil. The less the soil water content in the soil, which means we are bound to have more resistance. In other words, the stomata flows to avoid losing a lot of water. So we also did that measurement. Then we also, importantly, we also measured crop yield, which is a very important parameter. Can we go to the next, please? So in terms of our results and discussion, can we go to the next? We first of all looked at the soil water dynamics, and we looked at it on a seasonal basis. So in other words, we looked at each and every season to see what were the dynamics like. So far, we have been doing this kind of work for 3 seasons here in Zimbabwe. We started in 2018-19 season. What we saw from the during this season is that soil water content was slightly less in conservation agriculture compared to conventional tillage, especially from the soil depth of from 20 to 40 centimeters. In this kind of soils, this is like the typical effective rooting depth of for a maize crop. So we suspect that there was greater water uptake by the crop in CA than in conventional tillage. We will see from the results which are going to come to see whether it's valid or not, but we suspected that it was something related to this. Can we go to the next one, please? Then the following season, we also saw a similar trend to that observed during the previous season, where conservation agriculture, conventional tillage performed more than CA in those depth range, that is from 20 to 40 centimeters. Can we go to the next, please? So, sorry, you hear a lot of noise on the background. There is some fumigation which is going on at the top of my office. So at some point you will hear a lot of noise. Then in the 2020-21 season, the difference we saw in the previous 2 seasons was extended even to 60 centimeters depth. So in other words, in terms of the availability of water in these different plots, the conventional till was not that bad. It was not a bad option at all, because we saw that there were also more water in some depth in conventional tillage than in conservation agriculture. Though we suspected that in conservation agriculture there was more water uptake. Can we go to the next slide? Then in terms of stomatal conductance, there was no significant difference. So in other words, the plants under the 2 tillage practice were equally stressed. There was no much difference to talk about in terms of the the stomatal resistance. This is just confirming that water is not really an issue in this practice. Though we tend to get a slightly less resistance in conventional tillage. I think this is sort of agreeing with the soil water dynamics we realized, where conventional agriculture had slightly more water content, especially in the effective rooting depth. Can we go to the next, please? So in terms of leaf area development, we only measured this during the 2020-21 season, after realizing some of these issues with regard to soil water content. We realized that leaf area development is slower under CA, possibly is due to the initial immobilization of nutrients from crop residues. Remember, by adding the crop residues, there is always that tendency of crop residues locking the nutrients for them to be less available to the plants. Then later on, we saw some bigger values be emerging under CA. This was maybe due to now the decomposition of crop residues and releasing the nutrients. So this implies that more transpiration capacity, we had more transpiration capacity under CA, therefore a greater water uptake, which we reported earlier. So this is sort of qualifies the conclusion we already alluded to, that perhaps it was due to greater water uptake under CA. That's why we had less amount of soil water content under CA, especially within the root effective depth for the maize crop. Can we go to the next? So in terms of the yields, we realized that conservation agriculture yielded more than the conventional tillage. And with slightly less water, the benefit may not be related to water. So we feel, or we suggest that the benefit in terms of yield is less to do with the yield. Possibly it's due to some nutritional benefits, which is attributed to the addition of crop residues. So I think you have already seen the trend in terms of water dynamics. There was not much difference to talk about. Rather, conventional tillage had more water. So with regard to that, we expected more yield in conventional tillage than in conservation agriculture. If we are to pin our findings to soil water dynamics. So perhaps it's to do with the nutritional benefits which comes from the addition of crop residues. Can we go to the next? So in terms of our key message, we realized that soil water content is slightly less under CA in the effective rooting depth. That is from 20 to 60 centimeter depth compared to conventional T. There was high yield in CA compared to conventional. So we said it's likely due to nutritional benefits associated with the addition of crop residues. We hadn't thought about it. Perhaps it's a very strategic to have also some mount-based conventional tillage. Because remember, we saw slightly more water content in conventional tillage without crop residue. So we hypothesized that we would like to hypothesize that under mulch-based conventional tillage, we can get even better results in terms of soil water dynamics, even in terms of. This is just a very important question, which we have looked at in some other circles. And for now, I will leave it as it is. I know there are a lot of people who are against this idea, but from these findings, I think we are finding a pointer to that in terms of if we are to improve soil water dynamics as well as improve our yields. We can also have some mulch-based conventional tillage. It's quite strategic. I think we can explore this further. I think with that, this is the end of my presentation. I would like to thank you all. Kesile is my mother language. I'm a Shangan from Zimbabwe. Tatenda is Shona. Then I thank you is our English. Thank you, thank you, thank you.
Thanks for Ngai for your very interesting presentation. We are a bit short for time, so I'm just looking at questions. Richard has said that in season 2 there seemed to be an increase in soil moisture content in April, which was somewhat unexpected, and whether there was any explanation for that. I don't know, Alessia, can we just go back through the slides?
Yes. Sorry. Oops.
While Alessia is looking for that, I just see that there's Christian had a comment which Dee has forwarded to the Q&A. Thank you, Dee. So saying the presentation points to the need for long-term trials and comparable treatments between sites. That this leaves us with fewer degrees of freedom. Do we do multi-linear regression with different factors? So I'll take responsibility for answering that one. I agree that the need for long-term trials is definitely pointed to by these results, and having networks that allow us to do comparisons across different environments. I would also say I think this is also showing the importance of some of these standard good old style soil physical measurements, knowing not simply what the changes in porosity have been, but being able to tie them specifically to water tensions. In terms of integrating across sites with regression type models, I think there is some scope for doing that. I think also in the context of our of CEPHaS, we can certainly do some work combining some of the depth intervals we've got into directly comparable units, but local decisions were made there on the grounds of local conditions and what were known about the sites. I think some of the tools perhaps of used in meta-analysis for looking at experiments in the literature could be used similarly for applying to data from multiple trials across different locations where there are differences. And there's some very interesting ideas in Bayesian meta-analysis, which allows to make comparisons between treatments which are only perhaps linked by the fact that they have certain treatments in common at experiments. So you could compare one treatment with another when none of your trials have both, but where there is sufficient commonality between treatment A and let's say treatment C and D, and treatment C and D with your treatment B and other trials. So I think there are certainly approaches that could be taken for combining information from different trials. Right, now I don't know if we've now found the slide that Richard was referring to. April and season 2.
Yeah. So Ngai, are you happy to take this question? Ngai, you are on mute now.
Thank you very much, Richard, for the question. I think it's more attributed to some capillary rise of some sort. Remember, we earlier on I said this type of soils we tend to get some clay content increasing with depth due to elevation. So in other words, some clay particles are washed down. So probably it's related to that. I don't know if you are satisfied with that.
Thank you, Wengai. And just one last question, because we are running out of time. Do you know which nutrients are added by the crop residue?
Yeah, we really need to look at that. But I suspect in these soil types, one of the very important nutrients or a limiting nutrient is nitrogen. So I suspect that there is some little amount of nitrogen in those crop residues, which when added, we sort of improve that nutrient. It's in nitrogen and phosphorus actually. Nitrogen and phosphorus are very important. You tend to find a lot of phosphorus in some crop residues of some sort, especially of maize and some cereals.
Thank you, Ngai. We are pushed for time now. I see we've got some raised hands. If we type questions into the Q&A, then we will be able to come back to them either in discussion during the break or afterwards. So can I ask people to use Q&A to keep your questions in, because we are now going to have to move on. Thank you very much, Wengai, for your presentation. And our final one before the break is looking more specifically at conservation agriculture influences on soil organic carbon and aggregate stability. And this is some work which is being presented jointly by Dr. Kirsten Njira from Luana and Dr. Andy Tai from the British Geological Survey. So I'm not sure who's speaking first. I think it's Kirsten. So Kirsten will be starting the presentation and then handing over to Andy.
Thank you, Murray. I'll just put the presentation up.
Yes. Yes, okay. Hello everyone. Good morning. I hope you are able to get me.
Yes, we can hear you, Kirsten. Thank you.
Yes, I will present the first part of this. We have a number of slides. So I'll do the first part, a bit of a background, and I will continue. So next slide. Yeah, so this study is based on the State Research Station trials, that's in Malawi. And the idea was trying to look at the influence of CM on soil organic carbon and aggregate stability. So as a background, we understand that soil organic carbon is a very important indicator of soil health, as it influences soil fertility, soil structure, and moisture dynamics. So we felt a thorough understanding of the influences of CA on soil organic carbon dynamics can help us at least in the design of our CA systems. And soil organic carbon influences water holding capacity, soil structure, and soil aggregation, as I've said. And this helps to allow at least better root penetration and exchange of gases within the soil. Next slide. Yeah, looking at the soil aggregation. Soil aggregation happens as a mixture of these clay minerals, organic carbons itself, and including exudates and even glomalin from fungi. And these help to hold together clay and the organic particles. And when we look at soil aggregates, we see that a number of forces like cohesion and fragmentation forces may influence this both positively and negatively. As these aggregates are disrupted, then they will not be able to help in holding the moisture and the other important parameters in the soil. So we find that we need the aggregates that are giving some stability. So that was now the intention to check also aggregate stability as influenced by Ca. And this is also another important measure of soil health. Next slide, please. Yeah, so as aims, we wanted to assess how this year, by the time we were sampling these soils, it was 2017, and these CA treatments had been there for about 11 years. So I wanted to check the influence of CA on soil organic carbon concentrations and assess whether CA has produced changes in macro aggregates, and also to see if we can develop a conceptual understanding of the conditions required for macro aggregate formation in the soils. Next slide, please. Yeah, so the treatments, the trials, we have a number of treatments, but we only targeted 2. One on continuous maize, which we are calling T1, and the other one was a CA treatment with residue retention, but they were both maize monoculture systems. And these are in 4 blocks, and we sampled different depths, 0 to 10 and 10 to 30. So the diagram shows the sampling scheme. Yeah, let's next slide. So the analysis included the back soils and the organic carbon within the macro aggregates. So for the back soils, we had to measure the proportions of aggregates, different sizes in the back soil by dry sieving, and measure the concentration of soil organic carbon. Basically, we use the 3 methods for checking the extent of decomposition: delta carbon 13, laser fluorescence, and log level methods. So then we also check the mineralogy, and basically using XRD method. On the macro aggregates, we assess the extent of decomposition of the aggregate soil organic carbon using those 3 methods. And we also undertook aggregate stability tests using laser granulometer based analysis. And for statistical analysis, working group form, Mali and the working group 4 team helped in doing the statistical analysis. Next slide, please. Yeah, so looking at the question, does CA promote soil aggregation? We noted that in comparison between CA and non-CA plots, the differences were minor. There were some slight differences, which were pointing some positive influences of CA on soil aggregation. Next slide. Does CA increase soil organic carbon? This is within the aggregates. So what we noted that CA has some influences. Basically, this was concentrated on looking at the T3, which had some residues retained. So we noted that both the soil organic carbon within the less than 2 millimeter fraction and within the 1 to 2 millimeter aggregate, CA had some positive influences compared with the non-CA plots. So statistical analysis showed that there was some interaction with the treatment and the depth of sampling. Next slide, please. Yeah, so the other issue was to check the relationship between the aggregation and the mineralogy. So we noted that there was an increasing relationship as we go to the lower depths of the soil. So in these graphs, you find the red linear graph is indicating 10 to 30, while the blue one is 0 to 10. So I think this is the last slide to talk about, and they can take over from this slide. Thank you.
Thank you, Kester. Next slide, please. So one of the things we were interested in was whether there were changes in the soil organic carbon quality after CA. This is suggesting whether the carbon contained within the aggregates is of a different nature to that of the bulk soil, which may give an indication as to whether aggregates are, how they're protecting the organic carbon. So we threw 3 methods at this. We looked at the delta 13C, which it demonstrates normally when as soil organic carbon decomposes, the lighter isotope is used by the microbes, which results in an increase in enrichment in the 13C. As we can see from this graph, there was an enrichment in 13C at depth. There wasn't a treatment effect though. This is fairly typical soil profiles. The laser fluorescence looks at the number of phenol groups contained in the soil organic carbon as a measure of decomposition. We look at this as a humidification index. In the bulk soils at 10 to 30 centimetres, so the less than 2 millimetre fractions, the
humidification index is slightly less than in the 0 to 10 centimetres. This wasn't significant. In the aggregates, so organic carbon appears to have a higher humidification index than the bulk soils, with a treatment effect being found. This sort of backs up the 13C data. Next slide, please. So we come to probably a slightly more complex system, which is the Rockeval, which uses combustion to identify a immature I index, which would, and a refractory index of soil organic carbon. And as the I index increases, the general feeling is the soil organic carbon is less decomposed. As the R index increases, the soil organic carbon is more decomposed. Again, we're not seeing a huge effect here. We're seeing some groupings of samples, such as on the bulk soils, 10 to 30 centimetres on the treatment 3. But we're not really seeing a great deal using this. Again, we need to do a bit more work to understand quite exactly what each of these techniques is focusing in on. Next slide, please. So we also have used a macro aggregate test using a laser granulometer, which a colleague of mine developed at BGS. If we look at the diagram on the left-hand side, we can see that what we're looking at, so basically the test allows you to put 1 to 2 millimetre aggregates, 0 to 3 to 0.4 grams into the laser granulometer. At first, the outside of the aggregate would disintegrate, which gives you a water-stable aggregate, which we measure using mean weight diameter 1. The particle sizes then, particles in the machine are then sonicated, which disrupts the particles, and we measure this amount of disruption as as the difference between mean weight diameter 1 and mean weight diameter 2. And at the bottom, the diagram shows the size distributions as measured by the laser granulometer before and after sonication. And we can see that before sonication, you have more of a particle size distribution in the higher range. After sonication, you've shifted the particle size distribution to the left. So the more stable aggregates that you find, we calculate something called the disaggregation reduction, which is mean weight diameter 1 versus minus mean weight diameter 2. And this gives them, the larger this value, the more stable your aggregates. Can I have the next slide, please? So these are just examples of the particle size distributions from treatment 1 and treatment 3 at the 2 depths. As you can see, there are slight differences between treatment 1 and treatment 3, but not between the depths, but not with the treatments. Next slide, please. So we had a look at the properties, and we didn't really find a lot of differences, no significant differences. We did find that the DR2000 values were higher than for 2 catchments in the south of England, with these DR values for clay loam and a sandy clay loam are given in the right top corner. So our disaggregation ratios are higher. We've got to look into that. The other thing we've noticed that the median disaggregation reductions we found in the samples where we did, generally the treatment 3, the conservation agriculture techniques were slightly higher than their partners from conventional tillage. Can I have the next slide, please? We also found that there was a strong mineralogical control on the size aggregates. So we looked at all the aggregates from different depths together. And what we found in the mean weight diameter 1, which is the water stable aggregate, the mean weight diameter 2, which is the base soil aggregate, and also with disaggregation reduction, we had a much higher mineralogical relationship to size than we did than in the 0 to 10 centimetres. This suggests that possibly with more organic carbon in the surface layer, that produces slightly different aggregate stability properties. Next slide, please. So our conclusions. So organic carbon, there does seem to be some slight shift. We did find depth treatment effect at just outside 0.05 significance after 11 years. This does need to be put into context of conditions where microbial activity is likely to be high because of warm soils and organic matter inputs relatively low as compared to temperate systems. As I said, we did see initial sort of depth treatment interactions, both in the bulk soil and the macro aggregates. The measurements of delta 13C suggest there's an enrichment in 13C at depth, which is to be expected, no treatment effect. So we need to look into these different measures of organic carbon quality to understand precisely what is being measured and how they may differ. At lower soil organic carbon concentrations in the 10 to 30 centimetre depths, we see stronger aggregates with stronger mineralogical relationships to size, but we didn't see treatment effects in the water stable aggregates, the MWD1, the base aggregate size MWD2, or with disaggregation reduction between treatment and effect. There are suggestions that higher median values were obtained with treatment free. And we did find some relationship between aggregates, the size of the MWD1, 2, and disaggregation ratio to mineralogical properties, and this was mainly at depth. Thank you.
Thank you, Andy. Thanks for your talk, and thank you to Keston as well. I can see there's a couple of questions in the Q&A. We'll just take these quickly as we're running a little bit behind. So one from Richard.
No, that's the one that we've already.
Oh, sorry, that's been answered. Apologies. So only one question from Ikabongo. Isn't the difference of soil
organic carbon.
Sorry, between CA and TA, sorry, just due to residue addition in TA and not tillage? I think if residue retention is included in conventional tillage, there might be not clear differences in soil organic carbon between the two treatments. Any comments?
The lack of tillage would also mean that you're not disrupting the organic carbon which has been protected deeper down in the soil profile. So this hopefully gives it more protection against microbial attack, and one would hope that over time this may increase the amount of soil organic carbon in the soil.
Thank you, Andy.
So I don't think it's just, you've got two sources. You've got the soil organic carbon coming from the mulching, but you've also got this protection of all the root exudates, etc., that the plants are putting down deeper in the soil.
Yes, I mean, this is the sort of question that could be addressed by some of the factorial designs that I know CIMMYT has started to look at, where the different components of conservation agriculture are regarded as factors and factorial combinations. So you would have treatments where you were using conventional tillage, but also retaining residues. So that would be an interesting question to look at. Right. I see there's another question from from Russell. So he observed that the electrical response of the soils based on water content is varying with increasing depth. So it's not a constant relationship. It seems to be depth dependent. And he was suggesting that this might be correlated with changes in soil organic carbon and aggregation. I don't think he's asking a specific question, it's an observation, but I wonder if you have any reaction to that.
If I understand the observation right, so depending on the aggregation of soil, you would probably expect to see different responses in soil moisture. It also would link back to the moisture release curves. So I think that is that what Russell is after?
It could well be. Well, there'll be an opportunity to make some of those comparisons, perhaps. Certainly at Tretezi. Thank you. We're very glad to welcome as our second keynote speaker today, Dr. Christian Thierfelder from CIMMYT. Christian's based in Zimbabwe, and he has been a good friend to the CEPHaS project. We have enjoyed working together, particularly recently, well, I say recently, but in the course of the project, looking back at some of the data from the Tretezi experiment and seeing what we could extract from it with some longitudinal analysis and some power analysis. But Christian has been looking at conservation agriculture and just need to zip up one, I think, Alessia, to the slide. So is he there?
Yeah. Sorry, I'm just trying to share the screen.
Slide 5. Christian has been working with CIMMYT in the region now for some time. He has a particular interest in CA systems research and adaptation of agronomic systems to climate change, the identification of sustainable intensification strategies, climate smart agriculture, and increasingly, for those of us who follow him on Twitter, we've seen his interest in mechanisation and appropriate scale mechanisation, and perhaps an end to the backbreaking work of the hoe and the replacement with machinery to make agriculture more efficient and ergonomically acceptable. So we're very much looking forward to what Christian has to say to us in his keynote. The title that he's given us is Developing Resilient and Sustainable Cropping Systems for a Changing Climate, the Case of Southern Africa. So Christian, thank you very much indeed.
Yes, can everybody see my slide?
Yes.
Wonderful. Welcome everybody to this presentation, and as I was nicely introduced by Murray, yes, I haven't worked directly in CEPHaS. Actually, I have a similar project also called CEPHaS, but completely different, spelled in Zambia. But CEPHaS has been interesting for me because you do some of the systems research as well, going more into depth. My presentation is a product, an outcome of many, many partners. And I think the screen would not be long enough to mention them all, but I want to mention one in particular, Blessing Malanga, who supports me in the analysis of long-term trials and long-term work that we are doing. And this is particularly important because there's very few long-term trials in the region, and looking at CA systems from a longer-term perspective has many merits. For those who don't know, CIMMYT, the International Maize and Wheat Improvement Center, has a global mandate for maize and wheat-based science to improve livelihoods. We have more than 200 international staff. We are one of the CGIAR research centers with a global presence. We have 15 or so regional offices, and I operate out of the Zimbabwe office. The content of my presentation, I will first give an introduction into the subject, talk about conservation agriculture as a climate smart system, present you with some of the longer term results, share with you some challenges that we also observe. CA is not a one size fits all, and maybe some adoption questions that I want to pose as well at the end of my presentation. But let's look at the clients, the global audience that we are trying to address in Southern Africa. It's the smallholder farmer that we are working for. Those farmers usually are land, cash, and also knowledge constrained. They are mostly risk averse, often poorly connected to formal markets for seed, produce, machinery, and others. And they generally have low input and low output systems. So they apply little fertilizer and therefore also get little produce. And they are now confronted with a range of challenges. From the degradation point of view, soil erosion is a huge problem. Declining soil fertility is another one. And increasing impacts of climate change that you see in the middle. This was from an El Nino season in 2015, 2016. This is maize, not grass. It's almost at maturity level. And of course, farmers will not harvest anything from a plot like that. Then limited applications of nutrients in form of manure or mineral fertilizer adds to the low productivity. We expect that in 2 out of 5 cropping seasons, we have a drought. We also expect an increase in temperature from 2.1 to 2.7. And by 2030, we regularly expect a yield reduction of 10 to 30%. And by 2050, by 80%, if we don't have any adaptation to this situation. And one of the adaptations that we have worked on is conservation agriculture. Briefly again, the main principles: minimum soil movement, surface crop residue retention, and crop diversification. You see a few examples here. But in reality, conservation agriculture looks more like this. The 3 core principles need enablers and other complementary factors that help conservation agriculture work. We need good weed control. We need appropriate planting techniques. We need seed that is appropriate for this situation. Inclusion of legumes, fodder crops, agroforestry will increase the carbon in the soil. The use of inputs and soil and water conservation. You see positive and also negative effects of some of those effects. But it is important that we are not limiting ourselves to only those 3 core principles, because only those 3 principles will not make it work. When we started in 2004 in Southern Africa, we slowly developed from manual systems that you see on the top row, planting with a dibble stick or in planting basins, or sometimes also with a jab planter in Mozambique, towards more mechanized systems. In the middle row, you see animal traction systems with a ripper or with a direct seeder. And the newest is moving on to small appropriate machinery. You see in the middle with a single row direct seeder or with a double row direct seeder, all aimed at reducing the drudgery of farming and making farming more efficient under this situation. And CA can be many things. Maize under CA with grass residues, or a maize soybean rotation under no tillage, or groundnuts under CA. This is from central Malawi. Cowpeas under CA from southern Zambia. Maize pigeon pea intercropping, very common in southern Malawi and northern Mozambique. Or maize sclerotidia, which is an intervention that is being practiced in eastern Zambia to increase the productivity under low input agriculture systems. That's why we cannot just say this is CA. CA means many things. It has to be adapted to the site and farmer circumstances. Now, we talked about long-term effects, long-term benefits. And here you see 6 of our long-term trials from Zimbabwe, Henderson Research in Domboshawa, from southern Zambia, which is the Monze Farmer Training Center, from Malawi, which is the Chitezi Research Station, from Mozambique, Susundenga Research Station that we unfortunately had to stop because of lack of funding, and from eastern Zambia, Msekera Research Station. And you see very different responses to long-term trends. Some have a declining yield trend, and you will see in a minute why that is. Some are not performing very well. Some have good performing CA treatments that you see, for example, at Chitezi. All CA systems are actually having an increasing yield trend, while the conventional system has a declining yield trend. So you see it's very site specific. And most importantly, and the strongest factor is rainfall. Rainfall really affects CA systems over time, and they almost mirror what I've just showed from the yield response. That's why we really have a network of long-term trials, not only in one area, but across the whole region to really capture all these situations from very low rainfall to very high rainfall systems. Rainfall and the appropriate use of soil moisture is therefore a critical component. And especially when we look at climate change, climate adaptation. You see a conventional system from central Malawi that has just been exposed to a heavy rainfall. Most of the water that is seen there is standing in the furrows. And if there is a slight decline in the field, all this water will just run off and will be no use to anybody. It will just flow into the Malawi lake. And you see it very clearly in January, February, the rivers are all brown, and it will not be of any use to the crop. At the same moment, I took another picture here from a CA long-term on-farm trial. You see none of this water, it's all going into the soil, it's mostly infiltrating and benefiting the crop in times of dry spells or in-season droughts. And indeed, infiltration is a key factor and a key benefit of CA systems. Here I have results from 4 long-term trials. And you see one treatment always separating from the other CA systems is the conventional tilled or conventionally plowed system. It's clear that CA systems have a greater water intake. So, and that benefit is actually happening almost immediately. In the first or second season, you see already an infiltration benefit. Now, soil moisture is a longer term benefit, but even here you see over time, and this is a trial that has been running at the time when I used this data, it has been running for 6 years. It's now running for 15 years. You see a clear separation between conventional plowed systems and direct seeded systems. I put in a chat before, it's useful to look at the whole soil profile and not just at a single layer. So this is an aggregate soil moisture from 0 to 60 centimeters. So you really have the whole soil profile. And you see, of course, the treatments follow the rainfall that you see on the bottom, but one is separating again from the other treatments is the conventional practice, which gives us at the end a yield gain of 27% on a direct seeded maize soil treatment and a 53% yield benefit on a direct seeded maize cotton rotation. The adaptive capacity of CA under climate stress has been another focus area of our research. And I present this study that was done by Pete Stewart from Leeds University together with me. And we looked at both heat stress and drought stress at the same time using multilinear regression. And what you see on the y-axis is the precipitation balance. So negative values mean you have a drought stress. Positive values mean you have excess water. On the x-axis, you see heat stress, and this is standardized units. What it shows, when you have a soil with low clay content, which is the left panel, you see that under drought and heat stress, CA will always out-yield the conventional tillage practice. When you have more moisture, this benefit becomes less, and in some cases where you have a lot of moisture, the conventional system outperforms the CA system, which is the yellow-orange color. It is slightly different when you get to better soils, but still under drought and heat stress, CA systems are more favorable than the conventional system. That makes it climate smart. As you see, we are well prepared for drought and heat stress. We are not so well prepared for floods and waterlogging. And that's actually where the recommendation domain for CA lies. Here an example from the El Niño year 2015-2016 from our joint research station, Chitetse Research Station. You see both conventional practice on the right side and the CA practice on the left side. Both were planted on the same day. Both received the same fertilizer amounts and had the same seed. But there's a huge difference in productivity and crop performance directly related to low rainfall and lack of productivity because of that. We also looked at conservation agriculture systems in paired plots in on-farm trials across the whole region. So each dot represents a cluster of 6 farmers in each of these situations, looking at different types of CA systems. The one-to-one line separates the CA systems and the conventional systems. So everything that is below the one-to-one line is in favor of conventional tillage. Everything that is above the one-to-one line is in favor of CA. That means in 77% of the cases, we have a positive yield response when we look at CA systems. And in some cases, some of the treatments from Malawi and also from southern Zambia had even double the yield on the CA systems and crossing the 1-to-2 line. So you see, in certain circumstances, you really get good yield responses from CA systems. Economically, CA systems can also be more beneficial than the conventional practices. Here you see an analysis of 3 manual CA systems: dibble stick planting with continuous maize, dibble stick planting with maize cowpea intercropping, and dibble stick planting with cowpeas. And with maize cowpeas only in a rotation. And you see over time, and that's an analysis over 5 years, you see net benefits increasing as compared to the ridge and furrow system. Farmers are probably not so concerned on soil fertility. They're more concerned about monetary value of their cropping system. And this is a clear indication that CA systems can help them overcome cash constraints over time. The same applies for mechanized system using ripline seeding or direct seeding. Here, the maize soybean rotation was more favorable than the conventionally plowed maize soil treatment. Very clear results. So over time, we get also an economic benefit when we look at CA systems. But we have also limited knowledge about the mitigation potential of conservation agriculture. And I was very happy to see that in one of the presentations as well. Yes, there might be more efficient use of nutrients through a precision agriculture strategy when we look at CA. There might be reduced fossil fuel use. And also there might be some reductions in CO2, but there could be also an increase in nitrous oxides because of the increased biological activity, which leads to more microorganisms that exudate those gases. So very few studies so far have been done on greenhouse gas emissions. We are currently closing that knowledge gap through a collaboration with CIMMYT and also with the University of Kassel. But more needs to be done, and especially in the whole discussion, is CA an appropriate strategy to reduce greenhouse gas emissions? Also, we need more data. Secondly, carbon sequestration and a lot of the data that has been produced is a bit inconclusive. In some areas, under controlled conditions, we get an increase. Ligowe, for example, showed an increase from the Chitet research station, but everything was perfect there. Residue amounts were great. There was no livestock interfering, no or very little termite attack on the crop residues. So we got some increase in soil carbon, but on farm, I have rarely seen that. And there is potentially overstatement of soil carbon sequestration under no tillage. What we know already is that crop diversification is critically needed. It's one of the most critical components when we talk about carbon sequestration and soil organic matter increase. The second thing is often carbon accumulates in the first few centimeters and appears to be higher than it is in conventional systems. But it's mainly because in conventional systems, they are being tilled and plowed in. So they are more mixed in the first 30 centimeters. So there is really need for more research in that area. But what I said just now, what is really critically important is the effect of diversification. Crop rotation, for example, is the factor in the long term that gives us the greatest benefit. Intercropping, on the other hand, is beneficial. However, because there's always competition between a legume, for example, and the main crop, this benefit doesn't come out as strongly as it comes out with other interventions. So, and our work currently, because of the financial benefits that we also see from the intercropping, and farmers reluctant to dedicate 1 year of their crop to a rotational legume, we are working a lot or researching a lot on improving and stratifying intercropping systems. So how do we improve the integration of legumes into CA is the research area that a lot of work goes in at the moment. And a simple strategy, of course, is a maize groundnut rotation that you see here, a full rotation. But as I said, when you do that, farmers have to accept that they don't have a maize crop in the other year. And that is very hard, especially in areas where farmers are land constrained. So we work on intercropping systems, but the traditional way of intercropping is challenging because it leads to crop competition, and crop competition means reduction in maize yield. And that's what we are trying to avoid. That's why we are looking for options that farmers can use in their field to reduce that competition. This is, for example, an example that we are practicing 2-row strip cropping. You see here, we maintain the same plant population of maize, and but we plant it a bit more narrow than we usually would do, which opens up some plot area where a legume can proliferate. You see on the right right top side, you see a cowpea crop nicely developing without major reduction in yield on the maize crop. On the bottom, you see a maize groundnut strip cropping with groundnuts, yes. And again, you can see that both maize and groundnuts look very happily together without having too much competition. This can also be done in 4 rows, but we have already found out that the 2-row strip cropping is probably a better strategy. And then what I really want to stress here, we should not look at rotation and intercropping systems only from one crop perspective, let's say the maize. We have to look at both phases of the system. And here we convert everything into energy units. Both maize and legumes are converted, so they become having the same denominator. And when we look at that, all of a sudden a maize pitch and piece system outperforms a sole maize system, and the maize cowpea is at par with the sole maize system. So we are quite confident and very happy that actually when you look at the whole system and not just one crop in the rotation or the intercropping system, that you're getting a benefit. Now, let me talk a little bit about the main challenges with CA systems in Southern Africa. As I said, crop residue retention is important, but on the other hand, for farmers, draft power and livestock is equally important. It's an important component of the farming system as a security, a buffer, a source of nutrients, protein, and a sign of wealth in the status. And for some, in Malawi, small livestock is also very important. You see these mice hunters from Malawi, they burn our CA fields with nice crop residues because they want to get to the holes of the mice and dig them out. But it is, of course, terrible for the crop residues when they are all burnt. It's good for the mice hunters because they have a source of protein, but not so good for CA. Weed and its control, and we have published a lot on this topic. If you want more information, you can easily get it. The primary reason for tillage is to control weeds, and if you don't till your soil anymore, you have a weed control challenge, and that one you need to address with appropriate strategies. And that brings us to the Achilles heel of CA, which is the herbicides. Currently, it works very well when you use herbicides, but all the European donors and us as well, we don't want to see so much herbicide being applied because it has health and environmental side effects. So what we are trying to use is really to reduce the herbicide use, but then we need appropriate strategies to control the weeds, which could be through green manures, which could be through mechanical weed control strategies. And then the mindset of farmers often plays a big role. Doing away with the culture of the plow or soil tillage is a big step. We start with a small plow maybe in Ethiopia, this Maresha plow. Now plows become bigger and bigger, and you look at the UK, how big these plows are, and it seems that a farmer is only a real farmer if he has a huge tractor and a huge plow. And getting that out of the minds of the farmers is difficult. Aesthetics is also important. For southern Malawi, when you're not tilling or making those ridges, if you're burning or burying your crop residues, people look at you and say, but you have not tilled your soil, you are a lazy farmer. Getting that change of mindset is very difficult. And possibly the right place for a plow would be in the museum that you see on the top right. That's where it belongs, because we actually don't need the plow to do proper crop production. And that brings me to the last. There are many more challenges, but I've just focused on those. It's the adoption. The lack of adoption or limited adoption to CA in Southern Africa, which have some scholars questioning really the work that we are doing. It's not like we have it in Brazil or Argentina or the US. where really large proportions of the society has accepted CA, and the farmers are all implementing it. Here, it's different. And currently, we're probably at the moment at something like 1.5 million hectares under CA in Africa. And a recent study that we conducted in the target areas show that we are slightly better off in Zambia. There, farmers are adopting minimum tillage, mulching, crop rotation, to a lesser extent, intercropping. And what makes me very happy, also the integration of full CA in the areas that we surveyed, which are areas where CA programs and projects were happening in the past. So these are exposed areas. They are not nationally representative. They are areas where there were CA projects. In Zimbabwe, similar situation, a bit lower adoption of minimum tillage, but also high adoption on rotation. Mulching is less there, more crop livestock interaction. And unfortunately, lowest in Malawi, where we see very little minimum tillage. This culture of ridging is so prominent there. But rotation and intercropping is more practiced in these areas. But this is my second last slide. Transformational change is happening. And here I want to give one example from Zimbabwe. The Ministry of Agriculture has amplified manual CA systems to smallholders in the last 2 cropping seasons. Now, last year, they reached 2.2 million farmers with a technology that they call Fumbutsa, which is a small plot where they dig basins, retain residues, and grow maize. It's a starting point. We get many more farmers exposed to CA. But now we're moving into mechanization of these practices. And the permanent secretary already signed off on this and said, I want this. And he wants to reach 1 million farmers by 2025. And they even put already $5 million on the table for that. We are helping them to guide investment, what kind of machinery should be used, what capacity needs to be built and developed. We are proposing a service provider model so that we don't give a machinery to each and every farmer, but to service providers who can provide the seeding services, planting services, shelling, transport services to the farming communities. And this is considered to be a transformational change happening in Africa. There is a slogan by some organizations. They say the hoe must go, and I can only agree. Farming should be attractive, not only for old people, but also for the youth to get into. And they need to make use of all these options that we have. They are more modern and more efficient. And that's the end. I thank you very much for your interest.
Thanks very much indeed, Christian, for a very interesting overview. There are a couple of questions. I see Keith Goulding in the chat, particularly in response to your point on mitigation. We're saying, talking of data which have indicated increased bulk density under minimum or zero till. And we've certainly seen that on work here in the UK. And under those circumstances, you end up with an increase in nitrous oxide emissions from the soil. And that, of course, is bad news in terms of the overall greenhouse gas global warming forcing effect. Yes. One thing we found actually in the UK was at the same time we were getting increased methanotroph activity. So there was a reduction in the methane being emitted, which actually led to a net reduction, which draws attention to the importance of understanding not just one or two, but the whole suite of greenhouse gases that's coming out of the soil. We're hoping, in fact, in CEPHaS that we're getting some funding under a European joint programme to continue at our sites with direct measurement of greenhouse gas emissions, but we're still waiting on that one.
Yeah, indeed, as I mentioned in my talk, the whole black box of greenhouse gas emissions under CA systems under African conditions is still a black box to a large extent. But we have a PhD coming out of this and a master study that measured both in trials that have different CA components and also on farm to see differences and quantifying those differences. So I'm sure in the next 3, 4, 5 years, we have a much better handle on this. And I also think if you can get more funding, our long-term trials are at your disposal. I would really love to focus more on this work.
Thank you. And just one more question from Lydia Chabala-Hunza. She's asking about the potential of plastic cover mulches for weed control. And also saying to what extent can partial, she said, sorry, we can also report partial adoption as long as some aspects of conservation agriculture principles are included. So is the use of these plastic mulches for weed control something you think has potential?
In China, they use a lot of plastic mulch, and it's also practiced in some other parts of the world. For me, plastic is a bit of a no-go with a German environmental background, because you're introducing something that is not natural. But I'm not probably educated enough if they are biodegradable plastic forms that we could use and explore. I know also from other areas that they use stone mulch, which is an option as well, but equally farmers are not very happy, of course, to increase their stone level in their fields. You know, proper planning, the right cropping systems, inclusion of crops that also increase the residue amounts in the fields are probably the right strategies there. For example, in southern Malawi, northern Mozambique, the now traditional cropping system is a maize pigeon pea intercropping. And the pigeon pea can be used as mulch, if not used entirely for fuel or also. Especially if you leave the pigeon pea growing until the next cropping season, you then ratoon it and put it on the soil, and then you have a form of a mulch that can help. Partial adoption, yes, can be counted as a way towards CA. Often, unfortunately, it stays at partial adoption. So farmers practice one component maybe and never move beyond. And that is a problem, because you will never get the full benefit of a CA system, which only really comes out when you integrate all of these into one.
Okay, time I think just for one last question. Sorry, we won't be able to get them all in, but Spongaseni Mazabuko is saying, given that in South Africa you're getting at least 30% of maize residue consumed by livestock, how can we make the best use of the residue? Is there any work on how you can optimize the use of what residue you have for greater
Yes,
impact?
we have published several publications on that. Of course, partial grazing is an option. The problem is in Southern Africa that we have mostly free grazing systems, and the control of this is the challenge. Although there are bylaws in some areas, farmers let their cattle loose and then everything is grazed. But the problem is a different one. In my view, of course, changing the grazing system would be an intervention that would help. More importantly is that we don't have enough fodder for cattle, and high quality fodder, which would be much better for their physical structure and performance as well. So we only grow crops, but we never grow fodder. And that could be an intervention that has potential benefit. We are promoting green manures, for example, to cover for that. And in some areas, farms have really adopted that because they have seen that a velvet bean or a lap crop can produce 8, 10, 15 tons of of biomass that can be fed to animals in the dry winter season. And then we can keep some of those residues on the soil surface.
Thank you very much, Christian, and for your response to the questions as well as the talk. I mean, it's clear there's so many dimensions to these systems that we're only just starting to get to grips with in many ways, and lots of scope for inventive thought and creative thought about how to respond to some of the challenges. So it was really inspiring to hear you. So thank you ever so much again for joining us and for sharing with us. And apologies to those whose questions weren't addressed. But perhaps something.
I will address them now in the Q&A directly.
That's great. Thank you very much, Christian.
Okay.
Right. Now, the final item for today is just to introduce and, if it's not too grandiose a title, launch the CEPHaS Stat collection. And under Alessia, can I just?
Of course.
Thank you very much. I'm hoping I've got the slides here. Here we go. So are we sharing?
No, not yet. Sorry.
Sorry.
It's okay.
I'm aware that we have 5 minutes left of the official time, so I'll try to move through this as quickly as I can. Thank you, Alessia.
Okay.
That's now there. So CEPHaS Stat, Working Group 4 of the CEPHaS project is concerned with statistics. And there are topics in statistical research that we'll be hearing about later in the course of the conference. On Wednesday, CIMMYT will be presenting work that's been done looking at the evaluation of pedotransfer functions for predicting soil physical properties. And also on Wednesday, Ikebongo Mukumbutu will be presenting some outputs from the Instanza project, which was an allied project to CEPHaS, which was evaluating legacy soil information in Zambia specifically. We also did work modeling expert assessments of cropping systems using legacy soil data, and that was in a paper published in Geoderma. You can find the link there from the CEPHaS website publication page. We've also done work, and this was work along with Christian and CEPHaS colleagues in Malawi, looking at the full yield data set as it then was from Chitedzi, and looking at implications for power requirements for detecting yield effects in these settings. And we've also provided statistical consultancy within the project. And in particular, the example I've given here, at present, many members of the Luana CEPHaS team, along with DAR's colleagues in Malawi, are engaged in a survey across the country, collecting soil samples for physical measurements on intact cores and disaggregated material to get water release curves, and also soil carbon data, including at in some sites, soil carbon data down to 90 centimeters depth. So the sites you see there are on the map of Malawi. Blue sites are sites where we already knew through DARS that there was conservation agriculture practices adopted. So at each of those, there will be paired CA and conventional management sites investigated. And then the red dots represent other sites which will be visited for the same sampling. So this will provide national scale coverage, both for looking at comparisons between cropping systems, but also providing baseline information on soil physical properties in the country. So this sampling design was done by Working Group 4 to provide colleagues with sites. They're talking to farmers about their experiences, as well as collecting physical samples. And then in due course, there's soil samples back in Luana, and also some work in the DARS labs at Chitedzi will be analysed to provide both soil carbon information as well as physical properties. We've also given support in the analysis of groundwater and other time series data using generalised additive models, and we might hear a bit more about those later in the course of the week. But we've also attempted to deliver statistical training through sessions on the R platform. So at Network Meeting 1, we talked about design and analysis of experiments. From Network Meeting 2 onwards, we introduced daily R in response to feedback. People wanted more R, or perhaps what they wanted was it to be a little more dilute. So we had short, snappy sessions on statistics on a daily basis. And then in July 2018, July 2019, in fact, in Lusaka, we had an R Training and Trainers Day in which we talked about the delivery of statistical training and got feedback from all involved. And then in the course of the pandemic, we moved this all into an online environment, and we had R computation, statistical computation sessions. And here we've got a bit of our WhatsApp live feedback that we had during sessions to provide support. We've aimed to deliver everything through R as an open source platform, including training resources, scripts and slides and data sets, to provide early career researchers and others with an opportunity to reflect on the training process, statistical training, and to gain experience, with a aim to developing statistical literacy across the team, but also to provide long-term resources for the R platform. And this is where the CEPHaS stat collection of functions comes in. And this was shared back in 2019 across the project and has been used since and outside the project too. And the most recent version of the CEPHaS stat functions is available now from GitHub. I shared that link in the chat just now, but Alessia has also sent it out by email. So through that, you can get both the functions, but also documentation, example vignettes of the functions in use, and example data sets. And the functions are all described, or at least all the key top-level functions are described in R-style help files available in a PDF. So what I'm wanting to hopefully just show you now are one or two demonstrations in the R environment. Hopefully that's going to come up. So this is just straight vanilla R, which is my old-fashioned preference in these matters. There are a number of packages which need to be used, but we've kept those to a minimum for the moment. The mass package and then these other three here are all that are required. So we'll just call those for this initial demonstration. And then what we're planning to do in due course is to make CEPHaS stat a proper R package such that it can be downloaded from CRAN, but at present it's a collection of functions which can all be set up with a source command at the beginning of an R session. And here we've got a few examples, so I'll just take you through a couple. In the first one, we have a single set of measurements on the water release curve. And this is a nonlinear fitting function that CIMMYT developed. And if we plot our data here, we can see the water release curve for a single set of observations. So we're plotting the volumetric water content against tension. We give some initial guess values, and then this Van Gunukten fit single function in R will fit a water release curve to those data. And then having fitted it, you can add the function to the observations. Now this SQ indices, soil quality indices function, will then take in the water release curve data and then plot out a number of measures of soil quality based on that curve. And if you look in the documentation available on GitHub, it gives you full references and some description there. But we're looking, for example, at the plant available water capacity that the curve is indicating, or the air capacity, relative water capacity, which is talking about the saturation at field capacity, which in this case indicates the soil is rather dry at field capacity for microbial activities, and so on. Now, what we've also added in particular in the CEPHaS stat package is the use of a linear mixed model approach to fit different water response curves to observations from different treatments. So what we've got here, these are just data available from the WASAC Global Soil Database, available from ISRIC rather. And what we've got here are just some examples of some water retention curves fitted to feral soils and vertisols collected in Zimbabwe. So the question that we have is whether there is evidence that these water retention curves differ with respect to key parameters. So what we're doing here is saying that in our null model, we'll fit a common set of parameters to all our water retention curves data sets, and that in a full model, we will change all 4 of the Van Gunington parameters between the different soil classes. We can then fit the water retention curve, and this is done using a numerical procedure which is generating samples from posterior distribution for all the parameters, which is why it's taking a little bit of time. But eventually we get an output in which for our 2 soil types, we have our residual water content, our saturated water content, and then 2 parameters which are telling us something about the shape of the water retention curve and hence the porosity of the soils. And in particular here, what we're getting out are some inferential statistics about the strength of evidence for differences between those water retention curves. We can then plot those contrasting curves, as you see there for our different soil classes. And then we can look at and compare these soil quality indices between the different soil classes. So what we see here is firstly these properties output for the feral soils and then for the water vertisols. What you see in this case, in fact, is that despite the big differences in the water retention curves in terms of the absolute tensions, water contents at any given tension, in fact, the plant available water is not different. The difference between what's held at field capacity and what's held at the permanent wilting point, despite the shapes of the curves being different, is in fact about the same. But there are, of course, other differences between these soil water retention curves, which would come out if they were being used in process models. So I'll stop there because this is just to give you a flavour for some of the things that the CEPHaS stat codes allow people to do. They're available to everyone via that GitHub link. There are other things in there, including a lot on soil or general data exploratory analysis, computation of summary statistics, summary plots, and so on. So it's there, it's available. I hope you, the wider population, as well as the CEPHaS community, will find it useful, and by all means do get back to us. And there are in the documentation email links for myself, for Tracy, for Joseph, as first port of call for any comments that you might have, or queries that you might have, or suggestions that you might want to make. So I'll stop sharing there. And I don't know whether there are any particular queries or comments on that. As often said towards the end of a CEPHaS statistics training session, once you achieve saturation, any further input generally generates only runoff. So I won't generate any more runoff at this stage, but I am open to any queries or questions. But otherwise, I'll hand over to Alessia just to fill everyone in on processes for the remainder of the conference. But thank you all. So,
we can see a question, yes, so just check.
no, that's any statistics on groundwater levels? Yes, and I think you'll hear some more about this on the Friday session of the meeting.
Christian would like to answer a question live.
It's Christian. It says that you'd like to address this question on the Dandy raised antecedent conditions. Do you want to come on that now?
Yes, let me quickly understand the question. You know, it's a good question because it's a real limitation to CA. On the other hand, what we are trying to achieve with CA is an increase in soil quality. Also, we want to achieve reduced evaporation, increased water infiltration, and they are all directly related and associated with crop residues. Also, carbon increase, where shall it come from? If not from crop residues, and as to a certain extent also from diversification. So they are an essential part, although they are challenging. So what do? We give up, or we try to adapt the system or change the system. In other places, in other parts of the world, it took time as well. It's not unique to Southern Africa that crop residues are a challenge. But in most areas where CA has been practiced for a longer time, farmers more and more start to use crop residues as a means to improve their soils.
Okay, thank you, Christian, for that. I think we can draw the conference to a close for today. Thank you very much, everybody, for joining us. And apologies, we've run a little bit late, a bit behind schedule. But I think I want to thank all the presenters. You've done an amazing job, despite having been in various parts of the world. We've made it work, so thank you very much. And for the audience, I would like to ask everybody to fill out a feedback form, which I will be sending. And also, we will be answering any unanswered questions that have come in, and we shall distribute those as well. If you have any other that you want to send in, please use the CEPHaS email address, which you should have received with your Eventbrite invites. If you haven't received it, we can quickly put it in the chat for everybody to take a note for future reference. The next session will be on Wednesday. On Wednesday, we will be concentrating on soil properties and soil information. We have two external speakers again. You should all have received the program for the whole week. Please don't forget to register on Eventbrite so that you get your reminders and link for the Zoom. And thank you, and we shall see you on Wednesday. Bye-bye, everyone.
Thank you. Bye-bye.